We are now on chapter 3. We'll be covering only 3 sections like 3.1, 3.2 and 3.3 in this chapter. This is one of the smallest section-wise, and if you have understood the vector and if you have understood very well, I guess, how to resolve into x component and y component, then it will be easy to solve the problems. It's not difficult at all. I can promise you that. So look at this one. I have the first figure. The car is moving from rest right here with a velocity initially v0, and the final velocity is v. But here we wrote like r0 distance wise and r final for the final position, and this is your shortest travel or the displacement. So the displacement delta r of the car is a vector. It points from the initial position of the car at 0 it started, which is right here. Then final position is here. So we have the shortest distance, as you see, from here to here. Now we're going to figure out how to find displacement here. Displacement is delta r. It's again a vector. It has a direction. Is initial take away from the final position, and the velocity is same way, displacement over time, which is delta r over delta t, which is average velocity. Now we'll move on to the next topic, which is instantaneous velocity, which is similar to the one you had in chapter 2. V equals delta t tending to 0, delta r over delta t, and acceleration is change in velocity over time, delta v over delta t, and you have instantaneous acceleration where time tends to 0, and the equation remains the same, delta v over delta t. You'll be using the same type of equation as you did in chapter 2. Now look at this. Here you have the vector which you are going to resolve in direction of x and y, that you see this is your resultant matter of fact. Then delta will be delta v and vx, delta vy, but you don't do that here. It's only vx and vy. Now we're going to go to the next topic, which is 3, 3. Now look at this picture you have, where you have no motion in the direction of y, only the spacecraft moves in the direction of x. This is different, where you have motion in the direction of y, there is no motion on x. So matter of fact, if your vector is here, we will resolve into x and to y. Same way we did. Now we have the next topic, where I'll show you this picture here. Look at this. You have a component of velocity in the direction of x on y, so we'll find the resultant using the same equation. You have 1, 2, 3, 4 in chapter 2. As a result of the maximum velocity slowly starts from 0 and goes up to maximum velocity, where he is showing you the y component as well as x component. This is going on a projectile motion. I'll define projectile motion. What is that? Now look at this figure you have. It's showing you two components of the velocity, y component and x component. Okay, before we go to the final equation, this is the last section we have. And why it's called as projectile motion? It's something like a baseball, as in the home run. The motion of the ball, it's carrying the path which stands in a two-dimensional motion, and it is called as projectile motion. Consider vertical as y direction, horizontal as x direction separately, and do the calculation. You should go over the examples here in the book, which is example 4, 6, and also the first one is example 1 and 2. So these are the four important examples you can go yourself. Finally, now it comes in this table 1. He is defining you all the 4 equations entering in the direction of x and defining 4 equations in the direction of y. So you have x component and y component. All the variables are listed here in this table. This is very important to understand, which is similar to the one we had in chapter 2. That will be enough because we already covered section 1 to 3, the definitions, then how to resolve x component, y component, and projectile motion. Thank you. Have a good night. I'll talk to you again maybe in a couple of days. If you guys have more questions or more problems you want to know, but you should go over example 1, 2, 3, and 4 and 5. That's important. Thank you.